Hello friends, in this video uh, we will do workshop on uh, diff, diff pair, differential pair, and we will see uh, basically from in video lectures from 55 to 57 we have observed uh, or we have uh, learned about large signal behavior. So here we will see if we are increasing delta v in for diff pair, then how delta id, which is equals to id1 minus id2, how it is changing. So this behavior we will check, and basically we are taking one differential pair and we will find out how much delta V in required for fully switching current one MOSFET to another MOSFET. So this we will see in our simulation. So this workshop is related to differential pair large signal behavior. Okay, so let's start this. So here we are doing OP simulation. We are going to do OP simulation, and forget about this dot step statement. And as I told you in previous videos, we have taken tolerance and this X for Monte Carlo. Here we are not using, so I am taking tolerance 0 now. So we are taking here this diff pair, and here if I zoom this part, so here we are taking 1.25 as VCM, and we are giving 0 differential input. So V in 1 and V in 2 both are at 1.25. Say some current is here, say reference current is 10 micro, here we are taking 50 microampere current. Now our purpose is to find out whether current in both branches are same or not, and how much VGS minus VT is there, that is initial V1 value. After finding this, we are going to find out how much differential voltage is required to switch current from one MOSFET to another MOSFET. So here 50 micro is there, so initially it should be 25 microampere, and once we find out how much differential input is required, so after finding how much differential input is required to switch full current from one device to another device, so at that point of time, here in M1 left side device, in M1 full current, tail current will flow, in M2 zero current will flow. Okay, so let's do this simulation. So this is OP simulation. So I have already done this simulation and I have copied here. So here we can observe that VDD we are taking 1.8, V in 1 1.25, V in 2 1.25, both are 1.25, and V tail is at 389 or 390 millivolt. Okay, so let's start our calculation. So here VCM is taken as 1.25, V tail is 0.39, ID1 equals to ID2. So let's see how much ID1 ID2 is here. So this is basically 23.2 microampere. So this one ID. So this difference, actually tail current is 50 microampere we are taking, but because of this channel length modulation, it is only replicating I think 46 microampere. So let's see tail current. So device name, Okay, device name is M5. So M5 current, M5 ID, M5 ID, M5 ID. So this is 46.5. So okay, so for time being we can ignore that. This is because of channel and modulation. So our purpose is to find now what is VO on value. V on is VGS minus VT. Okay, here I would like to tell you threshold voltage for NMOS is 0.3075. So V on is VGS minus VT, VG is 1.25, source voltage means tail voltage is 0.39, and this is threshold voltage. So V on is coming like 0.5525. Okay, now we know differential voltage required to switch current. So that is V in is differential voltage square root of 2 of V on. So V on we have calculated 0.55. This will come as a 780 millivolt. This much is required. So half differential voltage we will give. So this is our differential pair. So half 390 millivolt we will give here, and minus 390 millivolt we will give here, because circuit is symmetric, and so total is 780 millivolt we will give here. So now initially V on 1 and V on 2 are same, which is 552 millivolt. We have just calculated. Okay, this is initial value, and now so when we give differential voltage, how much delta V on 1 will change and how much V on 2 will change. So for making this is say M2, for making this ID2 equals to 0, we want VGS minus VT should be equals to 0. So it means V on should equals to 0. So delta V on will be 0 minus this initial value 552 millivolt. So this is minus 552 millivolt. Delta V on 1 will be square root 2 minus 1, 552 millivolt. So this formula we have already calculated. So this will come like 228 millivolt. So it means V on 1 will increased by 228 millivolt, and V on 2 is reduced by 552 millivolt. Okay, and other thing is we will calculate tail node voltage, which will go up. We have already seen in our videos. So here we are finding out tail voltage increased by 162 millivolt. So tail voltage basically how we find out? So it is delta Vg minus delta V on difference. So using this method which we have already seen in videos, we find out delta Vs is 162 millivolt. So this is our calculated values: 552 millivolt V tail, and I tail is 50 micro, and M2 should be 0, and IM1 should be full tail current, and V11 is 552 and V12 is 0. So this we have already calculated. So V01 new value is this one. So new gate voltage, which is 1.25